Good morning.
Morning.
Yeah. How's your Labor Day weekend?
Not quite long enough.
Yeah, I know what you mean. I think it's weird how, I don't know why, like every university does this, but they usually have, one like normal day off per semester. And in the fall, it's Labor Day. And in the spring, it's usually Martin Luther King Jr. Day. And so it's like you do 1 week of class and then you get a day off. And I don't think there's really anyone who really wants to do that. I think everyone would prefer to have that day off, like, I don't know, on week 4 or week 12 or something. But I mean, I guess that's just when the holidays are. So. All right. Give these folks a couple more minutes or another minute or so before we get going. Okay. All right, well, got one more, so let's get started. So good morning, everybody. Hope you had a nice weekend. The announcements for today, there aren't too many, but homework 2, that one is due on this Thursday. Okay, so I think we were able to look at quite a bit of homework 2. Definitely plenty for you to be able to finish it up. We can spend maybe 15 to 20 minutes first today on any problems from homework 2 you're still having. But I think we looked at this set of problems. I think we looked at this and this. This one is fairly similar to this one, since you're just finding the divergence. We spoke about this one before we left last Thursday. Then the Laplacian, this is another one that you probably did many of these in your Calculus 3 class. These ones can also be solved using the cookbook. And then there's this last one, which is using the module. Okay. So this homework set is due Thursday. So just like last week, we will have a quiz on Thursday. So the quiz will open up for you to take at 7:55 a.m. if you want to start a little bit early. But basically, it just means that once you log on by the normal class time, it will be open. And then you'll submit it by 8:15, and then we'll get class started around 8:20. All right, so that's how the quiz will work. Again, the quiz will be one or two problems similar to something that you did in this homework. All right, any questions about this homework 2? All right, we'll begin homework 3 after that today. So we'll get started on homework 3 from about here on out. Let's see, it won't always be quite this way, but we'll start to get into a more of a normal situation where most of these homeworks, we'll work on them. We'll have a new homework, and then the next one will be due the next week. So that's generally what will be happening from here on out. So today we'll start on homework 3, which will be due on the 16th. So homework 3 is due next week. Okay. All right. Well, if there's no questions, let's see. Does anyone have any questions about homework 2? Do you want to work on any problems from homework 2 before we move on to homework 3?
I came in late, Dr.
Oh, okay.
Geisler. So the last assignment, the last number 8, you want us to download something from website to do that?
Yes, that is a good question. All right, so let's click on that link. And that will take you to this website. Okay. Do any of you have MacBooks, or any of you using MacBooks? No? Okay, it will probably be easier for you then, but I know for myself, I have a MacBook. You need to follow these directions carefully in order to download it. But you click on this vector analysis, chapter 3, and then just download this gradient one. And you'll need to click on it. And then it will give you a pop-up, or it should. But like I said, there's some specific things that you should follow. So for Mac users, it works a lot better if you do Firefox. Once you have that downloaded, you will get something like this. All right. Have any of you gotten this already?
Yeah, I was able to do it.
Okay, perfect. Yeah. So there's some different instructions. The main thing is it's going to ask you some security questions, because the publisher of this app is just the textbook website. And so you may need to do something to force it to run or unblock it. And that will be different depending on what machine you're using. So the problem is kind of an open-ended problem, but I wanted you to do this because it's kind of a cool visualization on how the gradient works. So you can select different types of functions, right? So you could select sinusoids, you can select exponentials and polynomials, and you can use these sliders to change the different part coefficients or parameters in the function, and you can see how that is going to affect the gradient of the function. Okay. So for example, on this one, I guess that doesn't make it any bigger, but on this one, right, I just moved around the parameters. And if you could visualize the surface, what does this surface look like? Can you visualize this surface?
I guess it would be like a sheet with a couple holes in it.
Yeah. So what part would be like the holes?
The red part.
So the red part, yeah, is where it's changing. If we're looking down, it's changing rapidly in that area. And then what is the blue part? So can you see what direction the arrows are pointed, like in this blue area?
Yeah, they're all pointed in on themselves.
Yeah, so in the blue area, the arrows are all pointed into the blue, and on the red area, the arrows are all pointed away from it. So for the red areas, let's see, those I think are, well, one of them is peak, right? And one of them is a valley. So this might look kind of like, do you know, have you ever seen like that egg foam type stuff? You know, that you could rest eggs in? I think that this whole surface should look something like that. It should have some peaks and then some valleys that are relatively round. So that's just kind of an example of the type of analysis that I want you to do in this problem 8. So determine where the function is changing most rapidly, least rapidly, and then describe the surface. So my description of this surface is maybe something like a egg crate foam or something like that. One more question, where is this changing? Where is this function? What areas is this function changing the least rapidly? Let's see.
It's changing the least rapidly in that green section and then also on the top of the red.
Yeah. Yeah. So right here, is this what you mean on top of the red?
Yeah, that's what I mean.
Yeah. So there's some point on top here, right, where it's like a peak or something, and it's not maybe instantaneously not changing. And then, yeah, so how did you determine the green area was the place where it's changing the least rapidly?
Because the green area is where it gets closest to 0.
Yeah, exactly. So you just looked at this color bar, and this color bar indicates that the green is right at the center, right? So we have -17 up to 17. And so the green is right in between there. And so that the green areas would be where this has basically zero change. Okay. Does anyone else have any questions about this problem or what I would like you to do? All right, so please don't use the sign. Don't use this exact same one that I did. You could use a different one, but you can change these, right? Change these sliders, and it should move, instantaneously, which is kind of interesting. I didn't ask you to do this, but you can, if you want, the other modules are ways of visualizing the other differential calculus that we've looked at as well. So they're kind of interesting to look at as well. Any other homework 2 questions? Okay, all right. Well, I will leave it to you to finish up homework 2. So that you can get all of that done by Thursday. All right, let's look at homework 3 now. So homework 3, we're now going to move into the chapter 4 of the textbook, and this chapter is on electrostatics. So the electrostatics chapter is kind of where the actual electromagnetics begins, right? So what we did previously, we spent basically 2 weeks, right, looking at vector calculus and reviewing vector calculus. And in the rest of this chapter, chapter 4, and through the rest of this book, we're going to see that the concepts that we reviewed with the vector calculus, they're going to continue to come back to us. So we won't ever be able to just totally forget about the vector calculus, but we'll end up using that throughout the rest of this this course, right? So many of the things that we're going to see, the relationships between fields and charges, they are going to rely on the vector calculus that we've already learned. So we will continue to use them. This one, in fact, right, this one is going to be similar to that, right? So this first question, already you can probably guess just by reading it, right, that this is going to be asking to use some kind of calculus, right? So we're given a volume in this problem, right? It says it's a round top cone, And we have a, what does this number mean? So this says rho V. What is that describing to us?
That's like how fast the electrical field is changing or something.
Yeah, it will have some effect on this, but it's this is a density, right? So rho is often used for density, and we can see that the units are in microcoulombs per meter, right? So we have units in microcoulombs per meter. Switch over to the PowerPoint. So this is actually a charge density. And when we look at this, there's different types of charge density that we could have, right? You could arrange your charges in many ways. You could arrange them on a line, on a surface, or in a volume. And this one is in a volume, right? So this is a volumetric charge density. Right, and so that's what this V stands for, rho V. And then we have a volumetric charge density, and we can see that it changes. This volumetric charge density changes as the radius changes, and also as angle theta changes. And then what is a round top cone? I'll give you a moment to draw this round top cone on your paper. So to begin this problem, sketch the round top cone, and then so begin the problem by sketching the round top cone so that we know where these charges are located. So we have a charge density inside of a round top cone. Take a moment and sketch the round top cone. If you need a hint, you could go to the cookbook, the vector cookbook, and this is, I'll just put this on a new page. Right, this is our spherical coordinate system, right? So you could find the spherical coordinate system if you need a hint. Okay, who has a sketch of the round top cone, or who could describe this round top cone? Let's see here. How about Cade? Have you sketched the round top cone?
No, still working on it.
Okay, what do you think? What does it mean with the round top part defined by r is less than or equal to 2 meters? What does that part mean? All right. How about Daniel? What does that mean? What does it mean to have the radius less than or equal to 2 meters?
My guess would be it's not gonna be greater than 2 meters, and probably it's changing.
Yeah, so if we drew, so we have a cone, right? And for the radius, it says it's less than or equal to 2 meters. So we know, I'm just going to sketch this, right? And let's say that this is 2 meters. All right. Now it says that theta is between 0 and pi/4. Okay, so Mario, what does that mean for the angle theta?
That's like the angle from the z-axis down, pointing down
Yeah, so
to the y. Yeah,
from z down like this.
yeah.
Okay, so from 0 down to pi/4. Okay, so then draw that here. It sort of seems like there's one piece of information left possibly that we aren't quite clear about, right? So we know that this is a cone, so what is phi going to be? What should phi be on this? Let's see, AK, what do you think? What should phi be?
Would it be 0?
So it's going to be a set of angles, and you're correct, it will start at 0. We could even write it, we can write it as 0 phi. And what would be the upper limit? What would be the set of angles? So if we want to make a cone and it has a round top, right? So this is a sphere. So we started with like a sphere, right? And then we said, we started with a sphere radius 2, then we cut into that and we said that the theta angle is pi/4. Now we have one last angle to define, and we've been told that it is a cone. So what would be that last angle phi that we need to, it didn't tell us it, but we can determine, we can know what it is just by looking. So if we want to make a cone, we need one more piece of information. So the cone up here, the cone starts here and it keeps going in this direction, right? When does it stop if we want to make a cone, if we want to make a complete cone?
It started.
Where it started, yeah. And so it would go all the way back around. And if we keep going all the way back to where it started, what would we call this angle?
Would that be 2 pi?
Yeah, by the time we get back around, right, it will be 2 pi over there. Okay. So we start at 0. Maybe right here, it's like, what, pi half. Then we get over here to pi, 3 pi halves, and then we'd make it all the way up to 2 pi. Okay. So now we have that last piece of information that it goes from 0 to 2 pi. All right, so if we were to draw this now, might look something like this, right? Where this is a rounded top. Let's see if I can, I don't know if I can, draw this exactly, but try to give it some surface looking, right? So this cone has a rounded top. It has a radius 2. So up here, right at this part on the top where I have it in black, right, everywhere up there, it reaches all the way out to a radius of 2. It has an angle of pi fourths, right? So when I measure from the z-axis down, right, I'm measuring from here to here to get this 0 to pi fourths. And then because we know it's a cone, we know that phi right here must stretch all the way around. Okay. And we're told that inside of this cone, right, there's some volumetric charge density. Right, so we have this volumetric charge density inside of that cone. And we want to be able to measure what the total amount of charge contained in that cone is. So what kind of integral should we do in order to get that total charge? So we have a density and we want to find the total charge contained. What type of integral should we do?
Is that just the a spherical one? Like I don't know how to explain it, but you have the charge up on
Yeah.
top divided by the 4 pi epsilon times the
Closer. So yeah, it is we'll do it in spherical coordinates for sure, because we have this it's in spherical. Now we want to find the total charge, and we know how dense the charge is in every area inside of that cone. So we need to look at every single area inside of the cone, and we need to add up all of the charge in that whole cone. So each point in the cone, we need to look at the charge density, and then we need to add that up over the entire cone. What kind of integral is that?
The triple integral.
Yeah, perfect. Exactly. That's exactly correct. Okay, this is going to be a triple integral, right? And it's a volume integral, right? So we're going to need to integrate the whole volume of the cone. And so that's going to be a triple integral because there's the 3 different directions, right? We have radius, we have theta, and we have phi. So we'll need to do an integral for each one of those directions. Okay, so that integral, right, should look like something like this, right? We're going to end up with a triple integral so we know this, right? And then we know that our integral is in radius, theta, and phi. Okay, so we need to know, so what we need to find are limits and dv. Okay, so take a minute, set this up on your paper. See if you can figure out what the limits are. And that's basically what we just discussed. And then also see if you can figure out what this dv is going to be. And if you need a hint, take a look at the cookbook, that vector cookbook, and that has a lot of information on all these integrals still. So try setting up this full integral. All right, so what's the limits on the radius? What should we have as the radius limits?
0 to 2.
Yeah, 0 to 2, because we know the radius. What about for theta?
0 to
5.
5.
Yeah. And for phi?
0 to 2 pi.
Yeah. And then did anyone get a dv?
That would just be r squared sine of theta dr d theta d phi.
Yeah, exactly. So, right, you could go to that cookbook, and this one, right, this is the one for the spherical coordinates. Okay. All right. Now you can solve this integral, right? So maybe some of you already started on that. But take a minute and solve the integral. So solve it using just your normal analytical method. If you get hung up, you could get out a calculator, or you could try Wolfram, if you need to, but see if you can finish up this calculation. All right, did anyone get to a final answer yet?
Yeah, I did.
Okay. Let's see, do you want, if you have a final answer, would you upload it to the Google Drive?
Okay, it should be uploaded now.
Not yet. Oops. Yeah. All right. So this is the answer that I get also, with one exception. What should the units be on this guy? So we just added up a bunch of charge. What are the units on that?
Shouldn't it just be coulombs per? No, it should just be coulombs, right?
Yeah, and it should just be coulombs. That's correct. It's not anything per. And then one other thing, this, if you kept this in microcoulombs, your answer here is probably going to be in microcoulombs also. All right, so let's take a look at this. All right. So did anyone else get this same answer?
I did get the same antiderivative. I just hadn't evaluated it.
Okay, cool. Yeah, it takes a minute to evaluate it, but this is what you should get when you do evaluate it. Now, a couple things to note, right? This is a triple integral. So when we do this first part, right, the r, when we integrate with respect to r, right, we only need to integrate, r is the only thing that's changing, so we can consider the rest as being constant, and same with the rest of the parts. If you are we're getting stuck, so hopefully, let's see if I can get this up here. So don't forget, if you're getting stuck or you have a hard integral on the homework problem, you can always go to Wolfram alpha, right? Just type in integral R4, r to the fourth. That would give you the first part of the answer. And then this likewise, right? If you did integral of cosine squared x sine of x, you could also get this result, right? So you could break this up and use Wolfram alpha to solve for parts of this, right? Or you could look in your old calculus textbook in the back, there's probably a big integral table. It might have this integral, it might not. Your calculator might also be able to do this, right? But you could use all of these, right, to combine these. So, and you could use the same steps that Calvin did, or you could break it up in different ways using Wolfram, but this is the answer you should get. So thank you for sharing, Calvin. Okay. All right. So does anyone have any other questions about this problem?
So, as I was watching the videos, so this isn't like because it asks for the total charge contained in the round top, this doesn't have anything to do with another point, right?
Yeah, this one does not have anything to do with the electric field. This one is just finding the total charge contained within a volume. Now we could use that similar information to find the electric field somewhere else, and that's what the next problems are actually going to be about. So you can use that, but that is the Coulomb's law, and this is just a little bit more simplistic way of analyzing this. So this could be like a you could think of this as an integral form of the Gauss's law. Okay, so jump ahead just a little bit because you asked, but it was a good question. All right, so we have Gauss's law is one of the ones the equations we're going to look at, right? And if you just take Gauss's law in the differential form, so if you find the divergence of the electric flux density, you will get a volumetric charge density. So do you remember what we said qualitatively? Like if you think about this, what does this mean? This means that if you look at this electric flux density field and you take the divergence of it, anywhere that it's not zero, anywhere that this evaluates as not zero, that means that charge exists in that area. Okay, so anywhere that you have a source of a field, so this is anywhere that you have the source of an electric field, which is related to the electric flux density, you have a charge volume located at that place. And if you want to know how much charge, right? Right, you could write an integral like this, right, which is the same thing, right? So hopefully this answers your question, Calvin, and then hopefully too for the rest of you, hopefully you've watched the videos, but just a lot of the stuff that we're getting at in this class is this relationship between fields, right? So fields are this is a vector field. It's a set, it's a bunch of information about the magnitude and direction of the electric field in space. And using information about the magnitude and direction of the field in space, you can actually also determine how much charge is in that space. So the charge is something that you could actually, see or touch, right? Like these would be electrons, right? Whereas the field is something that you can't see or touch this, right? But you can measure the effects of it. So this whole class, we're going to be looking at a lot of these relationships between these things, charges, fields, this type of information. So just completing this is kind of like doing and integrating over the differential form of Gauss's law. So that is a key piece of knowledge that we will use in this class and in electromagnetics to determine where charges are located in space. Okay. So does that answer your question, or did I just go on a tangent?
No, that answers my question.
Okay, great. So what about also for this problem, right? You integrated a volume, right? But what else could you integrate if you wanted to find the total amount of charge? go back to the homework. Right, so if you wanted to find the total amount of charge, what else could you integrate over? What other types of geometry? How else can charges be arranged?
You sheet zero lines.
Mm-hmm. Exactly. So you can have charges that are arranged in a line, we call it line charges. You could have charges that are arranged on a surface, that'd be a sheet charge. What's like a location that maybe you have seen a sheet charge in some of your other classes? Where have you seen a sheet charge?
On balloons.
Yeah, on a balloon. Yeah, that's a great place. There's another place too that you've another thing that you've probably seen sheet charges, or you could think of as a sheet charge, is a capacitor, right? That's two thin metallic sheets separated by a dielectric, right? If that sheet is covered in charge, right, that's a sheet charge, and you could perform one of these integrals to determine the total amount of charge contained on a capacitor, right? You probably did that in one of your classes already, or maybe in your physics class. So this total charge, it could be any different shape. This could be a volumetric shape, a surface, or a line, and you could have many different types of the volumetric, line, or surface charge densities. And the integral, if you wanted to find the total charge, would just be line, surface, or volume integral. Okay. Now let's go on to this question 2 about Coulomb's law and see if we can apply a bit of Coulomb's law. Okay, so we have two charges that are located in free space with these Cartesian coordinates. So you want to find the electric field, the total electric field, and then you're given information about a third charge, and then you find the electric field when all three charges exist. And then you add another charge and determine the force on the charge. Okay, so to answer this problem, you should go to the Moodle page, okay, and make sure that you have the Coulomb cookbook downloaded. Okay, so there is this one, Coulomb and Gauss cookbook. So if you don't have that, make sure that you go and get it, and this will help. This helps you to determine how to find the electric field due to charges. So this Coulomb's law is a way of finding the electric field due to a set of charges, point, line, surface, or volume. And this cookbook has a method, a 9-step method for finding that. And it also has some of the kind of more like rule of thumbs, the result that you would get in step 9 for a few simple cases. So such as if you just had point charges like this one, you could use this point charge method, or you could go through these steps on the cookbook. Okay, so I'm going to put you into breakout rooms. So in the breakout room, go there and start working on this problem using the Coulomb cookbook. All right, how are you both doing? Can you hear me?
Yeah.
Yeah,
Um, for A, like, I'm a little confused as to how to go about the problem. Or,
Okay.
yeah.
Yeah. So we have two charges and each charge is going to have its own electric field. Okay. So we have two charges. Each charge generates an electric field. And then there's this other principle that you've probably used in math and physics before called superposition. So if we could find the electric field due to charge 1 and the electric field due to charge 2 at this location, we could just add that up as superposition and find the total electric field there. Okay. Does that make sense? Does that sound familiar?
so we should treat them like they're point charges and then add it together.
Yeah, there are many ways to do this, but that is probably the easiest. Treat this as 1 point charge. So find the electric field at this point due to charge 1, then find the electric field at this point due to charge 2, and then add that electric field up together. Now, in that cookbook, there's more than one method to do it. This method is longer, but should get you the right answer every time. Okay. And it's really not that long. It's just more steps, right? And so, oops, this is the old version. Let's see if I can open a new version of this here real quick. Okay, there we go. So you could use this for point, line, surface, or volume charges, and this is a method for finding the vector direction at a new point, right? So you could use this set. So this is such a simple case: 2 charges, 1 point. You could use this location, this information, to solve for the field from charge 1 and the field from charge 2 and add them together. And you'll get this, or you could use, step 1 through 9 for charge 1, and you would get this equation, E1, and step 1 through 9 and arrive at this equation for charge 2. Okay. Or you could just, because it's so simple, you could just do this 2 charge method. But basically, right, you have 2 charges, and if you want to find the superposition of these charges, the total field, first you'll need to figure out a vector that points in this direction, right? So that you have this charge and you know that it's going to be pointed in that same direction, but you'll have to figure out what that vector is going to look at this point. And same thing for charge 2. And the steps would help you do that, or you could just use this and arrive there as is. Does that help you get started a little bit better?
Yes.
Yes.
All right, so I'll go to another breakout room, and hopefully that helps you. That cookbook is on the Moodle page if you need to go check it out again.
Right.
All right.
Thanks.
Yeah, you're welcome. Hey, AK, just you, is Gabriel gone?
Yes.
No, okay, sorry, I didn't have the gallery view. How are you guys doing? Have you got this figured out?
Working on it.
Yeah. So there's more than one way to solve for this, but the idea is that you have 2 charges. Each charge in space generates an electric field. You can add the effect of those electric fields together using superposition to get the total electric field, right? So the total electric field, right, is the sum of the field from charge 1 and the field from charge 2. So the easiest way to do this is probably finding the electric field due to charge 1 at your point, then finding the electric field due to charge 2 at your point, then add those together as a sum, and you will get the total electric field at that point. So I think, is that, it looks like AK, you got the location of charge 1, location of charge 2, you got the point, and then it looks like you are making some vectors, right? So that you know the direction of the field due to charge 1 and the field due to charge 2. Is that basically what you're working on?
Well, that's Gabriel working on it.
Okay,
but,
this is Gabriel's work. Okay.
Yeah, but I'm still in the middle of it. I'm still working on it. So
Okay, so let me just point out one thing too. First, please, be sure to use the vector notation for our class in this class. And then if you don't mind, I'm going to share my screen. In this cookbook, there's steps for both of these. So you could do this. This method is a little bit longer, but the steps are the same no matter what set of charges you have. And so I like this method because it's it doesn't change. It's a little bit longer, but you can always get the right answer. Or because this is a very simple case, 2 charges, 1 point, the final results of these steps are included down here. So you could use this method also. But you have, right, in this situation, it's a slightly different geometry, but it will look like this, right? You have a charge 1 and a point, and you want to find the electric field due to that charge. So that means you need to find the direction of the field, right? So you need to find a vector that describes the direction and the magnitude of the electric field due to this charge at this point. You also need to do that for charge 2. Now you can follow the steps up here, and these steps will give you a vector, this RSP. This vector is a unit vector that shows you the direction with a unit vector magnitude of that electric field due to that charge 1, and then you repeat for charge 2. Or you can follow these steps. So take a look at this cookbook and choose one of these methods. If this looks confusing to you, I'd say just start up here in this. And then if that's still confusing, make sure that you've watched the videos, because the videos will also describe to you exactly how to use this method. All right. Any questions I can answer? All right. Well, I'm going to go to the last breakout room then. So I will see you later.
No. I didn't have anything to say.
Hey, Calvin and Cade, how are you doing? You hear me? Not good?
Well, I mean, we have
Doing all right.
an answer. So, okay, electrical fields always come out as vectors, right?
Yeah, so just even that word field means vector field. It's short for vector field. You could think of it as being short for vector field.
Okay, so, well, we got an answer, and I guess it makes sense. It's only in the z hat direction though.
Okay.
Part A.
Yeah, let me see if I can remember what direction it is. And I think, yeah, it is only in the Z direction.
Okay, so
Yeah.
I think we got the first part then.
Okay. Yeah, it just so happens that the X fields, they cancel out. And
Okay.
does that make sense? What do you think they should cancel?
For me it does, because they're on opposite sides of the, but I just thought since they're both in the X and then the one is in the Z, Yeah, I thought that there would be a y component at least, but
Yeah. Yeah, and if we moved the point that we're looking at, the y component could show up, but this, what you're saying, right? The cancellation brings up this important point that when we deal with electric fields, they follow the property of superposition, and the superposition property is something that we've used it in physics, you've used it in math, we've used it all over the place, but there's certain things like these electric fields that they sum up. So you can find the electric field due to one point and another point, add them together, that's superposition, and then you get the total electric field. So this idea of like them canceling, right? That is just saying, okay, if we choose a special geometry where there's symmetry, we can get on the symmetrical area, we can get cancellation of the electric field because we're summing the electric fields together. We're summing them together. So if you have, one on this side, a charge on this side, a charge on this side, their fields point in the same direction and they would cancel out. And we'll see this with some of the other fields we look at as well, but this is especially applicable for the charges. And then, yeah, why doesn't it have the y? I think it's just the charge direction or the geometry
Yeah.
that we're in.
so okay, then part B isn't that much harder. It's just adding another one.
Yeah.
I actually had a question as I was watching the videos. I got really confused when she started doing she started changing it from like the squared on the bottom to the cubed on the bottom, and then she had a different vector at the end. And that one was just harder to follow for me.
Okay. Yeah, great question. Let me try to let me pull up the cookbook, see if I can answer that quickly. But basically, the reason for that is these two are equivalent. You can have, you have to know the direction that the field is pointed in, and you can either use a unit vector multiplied by this, or you can use a vector divided by the triple magnitude. And the reason for that is because a unit vector is the vector divided by the magnitude. So
Okay.
that's where that comes from. Yeah. So let me bring everyone back together. But yeah, great. Let's see, leave room, close all rooms. Yeah, so that's where that comes from on there is just the different ways of defining a unit vector. But ultimately, you need to know the direction, and you can either know the direction via a normal vector or by a unit vector. And so there's two ways of expressing it.
Okay.
Yeah. Okay. Maybe everyone else. May have left, I don't know. Yeah. Okay. Well, anyways, yeah, the class is over. We'll look at this problem more next on Thursday. It takes a little while to get used to all this, and we'll look at it in a little bit more detail, but that the cookbook has two ways of looking at it. One is, oh, everyone else is. Okay. All right. Hi, everybody. So thanks for joining back. We're going to keep looking at this problem again on Thursday. We'll look at it in more detail on the cookbook, but basically the idea is superposition. So make sure you watch the videos. The videos do show how to do many types of these problems as well. So that should give you an idea of what we're doing here. All right. Thank you. I'll stick around if you have any other questions. If not, you're free to take off, and I will see you on Thursday at 8:20 after the quiz.
Professor Chrysler. I have a quick question. The videos shows like the formulas to use, but doesn't exactly keep like the applications for it. I was wondering if we could like do that maybe next class or something.
Yeah, the videos don't what? I didn't.
They give like the formulas for it, but like they don't expressly like use an example.
There are examples in the videos. Some of them are examples. Yeah.
Or Coulomb's law.
Yeah, there should be a Coulomb's law example video. We will work on this some more, but let me just go back and look real quick. There should be some examples though. Let's see. So yes, let me show you here. Right, this one, Coulomb point charges example. So if you go to that fourth video, that one should be an example video on how to do this.
Writing's not that easy, but Grammarly can help. This sentence is grammatically correct.
Now let's do a specific example.
So
I'm going to do
this
this
one,
in
yeah.
2 dimensions.
this one is a specific example for you. And she has these charges, the charge here, and then the point here, and she finds the electric field due to that, to this point. And this,
she did, but then she introduced like the superposition formula towards the end of the video, but didn't actually use get that. So she solved it using like the formula you showed us, the 7-point thing, like the step-by-step thing.
Mhm.
But then she gave the formula for superposition, which was the summation of point charges and using using the unit vector summation UI, that formula, but she didn't use it in the example. I don't know.
Oh, okay. Yeah, so let me pull up a whiteboard here. So for superposition, let's say we have field E1. Okay. Let's say these are our two fields. Okay. So the superposition E is, sorry, E1 plus E2. Okay, and so to do that, we'd have an X direction, and that would be this plus this. So I'll do it even in another color. Okay, and then the Y. So what the superposition is saying is that you just add all of these up. So it doesn't matter what field E1 and E2 is, you just add them together. And we could add in another field, right? Even if we had like E3 that had AX3, we would just add it in here. And the superposition is saying that the fields just add together. So once you know the field in each one of the three directions for your coordinate system. So in this case, we're in Cartesian, so we just need X, Y, and Z. If you're in cylindrical, if you had R phi Z, you know, as long as you have those three, you can combine them, you can sum them up. You can sum up as many fields as you want, and you will get the total field at a location. So the superposition, it just means add everything up at the point that you're interested in. Does
So
that,
after adding it up, so instead of just using AX1, AY1, AZ1 in the formula, I would use AX1 plus AX2 plus AX3 to represent X direction in the formula.
yeah, so whatever your two, like if you have two fields, yeah, like this could be, you know, whatever this is, 5, 6, -6, whatever it is, you just add these coefficients together.
I got it.
And in this case, on this problem, this isn't quite how ours is, but right, we have like a charge here and a charge here, and then we're looking here, right? So let's say this is P1. So this charge, if these are positive charges, the field will point away. Okay. So then the field, let's say it's here. Okay, it should be X, Z. All right, so for these two charges, let's say they're both on in the X is 0 plane. So let's just forget about this. But do you see how this one, we can, this would be E1 Y, and then you also have E1 Z, and you can break it up into those two parts, and then you could also break up. Sorry, I'm trying to get some good colors here. E2Z and E2Y, and these two are going to cancel out, right? If they're the same magnitude, let's say that, you know, just like 10 coulombs and 10 coulombs. So then E2Y is equal to minus 2Y is equal to E1Y. So they're going to cancel out, right? This one is pointed left. This one is pointed right. So they're just going to cancel out because they're the same magnitude in opposite direction. So for this case, right, the E total only contains the Z direction. And it's going to be, you know, E2Z plus E1Z. Does this make a bit more sense?
Yes, it does. It does.
Okay.
I just needed to get how to apply it, but I get it now.
Okay. I think this video, the next video, I believe this one.
Hi, welcome.
It also describes more about superposition as well. And and this one has a bunch of animations on how, you could have tons of charges and put them together for superposition.
And the thing is, like, I've seen all the videos already, but there wasn't one where they actually used it. Like they talked about it, they talked
Okay.
about the graph, they talked about, but there wasn't one where they actually like used it to solve.
Okay. Yeah, and yeah, so we'll look at it a little bit more too on Thursday, like how to actually use the numbers on it.
Thank you.
Yeah. Yeah, thanks, Daniel. Hope you have a nice day.
You too.
See ya.